Alright, hello. So tonight we're going to be looking at several things, mostly regression, what it's called. Regression is that idea of fitting a curve or a model, and by model we mean really a numerical model, so it could be linear, it could be curved, whatever, to data. Okay, that's the game of it. So what we're going to do, I have some data here, some heights, people's heights in inches, mins, and their weights. And when I graph it, I see this thing here. Okay? Now I can clearly add a trend line to this. Linear. Boom, boom, and a boom. And as you can see, this trend line, it is what it is. There it is. So when I look at it, I think it's not a great trend line at all, for one thing. The other thing I want to see about this correlation has positive slopes, so I'm going to do the square root of 0.1851. 0.43. Okay, now we're going to test that in a minute, just like we did the other day. We'll see if that's significant or not. But for all intents and purposes, this doesn't look very significant. Okay. Notice how that in the middle it's all over the place. On the ends it's a little tighter. Now, that's just weird, by the way. Excuse me, because when I generated this data, I did it on purpose. I added in some crazy error there. But what you'll notice is when you look at this, it's kind of weird in that if you look at the middle, it's more weird, more strange, more open. Doesn't fit the line as good. So if you go to data analysis like we talked about last time, I'm going here to regression. Okay, now this is important. When you're doing regression, they will always ask you for the y's first. Pretty much in every program ever made, y's come first and then x's. Now notice I did not take the labels with me, so I'm going to fix that on this one here. So go from B1 rather. Excuse me, I do have labels. And I want to keep the residuals. I'm going to go ahead and get standardized residuals just for fun. I want to look at residual plots. Okay? And I'm going to go ahead and hit OK there just to see what happens. Okay? So what we're going to see here is, this is just another way of testing this. Okay? Well, you'll see right here, there's your 3.5, that is your slope. There's your y-intercept, okay, just like before. And here's your r squared, and then there's your r up there we already calculated. Okay. So a different test for this is what's called an f-test. It will tell you 100% the same thing as what the t-test tells you. Okay. And so it's a slightly different way of going about it. You would have used a t with 29 degrees of freedom. An F with 1 degree of freedom and 29 degrees of freedom will give you the exact same result. I call them kissing cousins. They're very closely related. So the probability of that happening is 0.01. What do you mean what the probability of happening? Well, H naught here is that there is no correlation. So I'll call it big P, so rho equals 0, versus, of course, H1, which, of course, is rho not equals 0. Actually, I don't know how to write that. Not equals 0, because I don't have my other. Oh, I wanted to do it in this computer because I wanted to be able to generate data quickly and moving around fast. With my little tablet, it doesn't work as nicely. Now, the reason we look at residual plots is it's just a different way of looking at, if you will, what's going on. So here we're saying that there's very little error on the outside. But in the middle, the error is quite weird. It's all over the map. Quite a bit high here in the middle in this little range, and we're low here for some reason on this part here. Okay. So I'm going to splice a couple pieces of video together for this video, and actually I don't know. I might do two-part video to this. We'll see how it works out. But when I look at that, that's what I'm looking for when it comes to residual plots. The idea being, if I were to predict from this graph, which I'm not going to, because look at this. That's so small, I'm going to reject H naught. I'm going to reject that guy. And by rejecting it, what am I going to do? by rejecting h naught, we're assuming that the correlation is not equal to 0. Okay? And so it is a pretty significant test in this situation, which when you look at it for initially, you're like, geez, 0.4, it's not a great deal, but it's okay. Now, the t-test we talked about the other day was equals, and if you'll recall, it's on page, I'll look it up for you in your book here. Ouch. Oh, where are you? T-test. There it is. No, it's not. Yes, it's R. So the correlation, which was 0.43 divided by parentheses, and it's the square root of, I should just do that, square root of, and then parentheses, 1 minus R squared, right, divided by, inside of that square root, the degrees of freedom, which was 29, right? 1 minus R, correct? Or n minus, I'm sorry, n minus 2, what am I thinking about? N minus 2, which is 28. Yeah, oh, that's right, you'd have 28 degrees of freedom, I mean, 28 degrees of freedom for the t. So you get 2.5, alright? That's my test statistic, okay? So if I do equals t dot inverse, okay, probability, so if we're doing this at 0.05 level of significance, 28 degrees of freedom, I'm going to get negative 2.048, plus or minus. So if you draw the picture, there it is, like so. Whee! 2.04 negative 2.04. 2.5 is out here in the tail, so you're going to reject H naught, and you're going to go with H1. In other words, it is a good fit. Now, what we're going to do, we're going to talk a little bit more about this tonight in terms of, all right, well, that's nice. What would be our predicted values? Well, I could do what are called the predicted values. You can also call them, they are called the fits sometimes because you predicted them. They're from the model. That's why the model fits the data. So according to this, we're going to take equals 3.53 times the height minus 73.242. That's the predicted value. Okay? So you notice that we're 2 pounds under at this point. What this is saying to us over here. This little top blue diamond right there, no. This blue diamond, where did it go? Which one are we on? Oh, because I'm not on the right one. 69 is over here somewhere, yes? So there's 68. Give it to me. There's 69 and 1.72, right? Under 72. So notice how that diamond is just above the line. The line is at 170, right here, if you're on that line. But the actual value was 172. Paste these down. Now to find the residuals, you're going to take and do the following. You're going to do equals. It's always exact or actual value minus predicted. If it comes out positive, that means this actual value is above the line. Okay? And if it comes out negative, it's below the line. Now, what a person can do if they wanted to, so what I want to do is take my cursor here and I want to highlight column A. And I want to hit Control, hold it down, and I'm going to highlight column D as well. Okay? And so what I can actually do, oh fart, sorry about that, let's try it again. Control, highlight this fella here. And we're going to go to Insert, Scatter Plot, boom. And you're like, whoa, that's a crazy graph. It's very similar to this graph. It is very similar to this graph, except what happened here. Okay? So, this is our actual values, right, this is where our actual values on the curve. What is this over here? This thing over here is the actual errors. I'm graphing the residuals. Wait a minute, I've seen residual plots. Hey, it's right here. Notice how they went from negative 50 to 50? Right? Mine's that way too. It just looks a little different the way mine is. But I have the exact same basic shape as this one over on the other page. Okay, and that's what's called a residual plot. Now, based on how Excel has rendered this one in terms of negative 50 to 50s over a narrower area on a graph this way, theirs looks different than mine, but I can make it bigger by stretching it out, of course, right? And I give you, voila, it's the same graph, yes? Now notice when it's stretched out, it doesn't look as bad, but again, we are off here in the middle. It's not as good a fit as it is out toward the edges. Out toward the edges, it's a little bit better of a fit. Okay, so again, bottom line here. I find my scatter plot. Always find your scatter plot. For goodness sakes, always find your scatter plot. The original scatter plot of the x's and the y. Fit the trend line to it. There's r squared. It's going uphill, so when you square root, you want the positive correlation. Go ahead and test the correlation like we did the other day with the t, or you're welcome to use, in the data analysis tool package, you're welcome to use the regression function. If you're going to use the regression function, okay, if you do that, which is totally fine with me, I still want the original graph. The original graph should always be up on your paper somewhere so you can look at it. Always get a residual plot. That residual plot is going to help us in terms of knowing, hey, I can make a plot, and out here on this end of it, it's going to be a better estimate. It's going to tend to be a better estimate than if I'm in the middle here. There's going to be a lot more uncertainty when I'm predicting around x equals 70 or 71. I mean, they're going to be a little weirder. In other words, these shorter guys, they tend to follow the line more closely. But when you get up here around 6 foot, it's at 5'11", 6 foot, you got some really chunky monkeys and some, well, mostly chunky monkeys, huh? And a few scrawny guys too, but mostly some fatties up here, right? So just something to think about so that when you analyze your data, hey, is this a better deal or whatever it is, okay? We can actually see how well it fits. And again, these are just our residual plots. In the old days, I'd make people do their own. Nah, I don't think I care anymore, okay? Now, I'm going to show you something here, and you're going to go like, can I just generate this data myself? Well, you could, but that's goofy. So age and number of lines on face. I don't know. So I'm going to generate some ages, and I'm going to start, or we're going to do like for some, I don't know, teachers who've been at it a while. So I don't know, I'm just going to pick a numbers here. And so I'm going to generate, let's generate 50 people this time, in a normal distribution. And I'm going to have that their average age is 60 years old. Standard deviation of 15. Sounds good to me. And let's generate that data, and let's put it in A1, or A2 rather. Boom. These are people's ages. Now, you're not going to be required to do this part. I'm just showing you how I come up with this data because I want you to see in a moment, because part of regression is based on a theory that's a pretty big deal, and that's what we're going to talk about next. And I don't know, I could tell you it, or I could just show you the idea behind it. And so, oopsie daisy, big dummy. Try again, stupid. There you go. Alright, so these are people's ages. So what I'm going to do is I am going to click on this. I'm going to sort it. Oh, shut up. Leave me alone. No, continue. Leave me alone. There we go. So we went from age 18 up to age 86. I think we feel fairly comfortable believing that the older we get, the more laugh lines we get. So our lines or whatever. I'm going to say we gain 1.3 lines per year. Okay. Alright. And we start with like, I don't know, we start with like, I don't know, 2. I don't know, whatever that means. Okay. Plus 2, whatever that means. I don't even know. Now, I could do this and I could generate it on the page. And if I did this, I'm going to go ahead and do it just for fun, just for a good time. And so I'm going to hold control down and drag this guy up like so. And I'm going to go scatter plot, and you're going to go, oh my gosh, it's perfectly linear. It is. And when I make this trend line, it's going to have an r squared that's 1. Friends, it's not that. It never is that way. So what we're going to do is we're going to do something that's kind of cool. So I'm going to say, oops, I'm going to come over to this data. Oops. Because part of regression and analysis is the theory that there's always what we call error. Oops, I clicked on the wrong thing. There's always what's called error. Okay? And so it's that idea that no matter what value of x you go to, we get what's called a normal distribution again. So when you're a 36-year-old, okay, there is a average number of laugh lines on this person's face. There's an average number of them. Okay? And so when I write this equation in a few minutes, y equals, and we're going to get some dumb equation like this in a couple of minutes, and you're going to say, okay, cool, plus 34, or whatever it is. Whatever it comes out to be, this y, so when I put x equals age 36 in, okay, I will get some number out, which is the average number of lines for a 36-year-old. Okay, same thing will happen at 38, 39, 40, and so on. But here's the thing. If you look at only the people who are age 36, and you said, let's get a bunch of 36-year-olds in here, let's count how many lines on their faces there are. Well, that would just be the normal distribution we've always done. And we said these people all have the age 36 in common. And so, in other words, when we draw this line, not that line, try this line. This line through here, if you go to, let's say, age 36 was along this line right here, if you take those values and then lay them sideways, what you should end up with when you graph them is a histogram that is normal bell-shaped. And that will be true no matter where you are on this graph. Now, we only did a few points on this one, like 30, so it's not going to be as much. Now, here's the deal. For all values of x, they will share the same standard deviation. That's a fact. And so we're going to get some normal distribution. Okay? And so what we're going to get is we're going to get that y evaluated at the age in question, comma, some standard deviation. Now next week in class we're going to talk about, well, how do we find this standard deviation? We're going to worry about that later, not tonight. But the age we are going to worry about tonight. So if I say to you, what's the mean, how many lines are there on a 36-year-old's face, you're literally going to drop 36 into here, and whatever you get out is going to become that average. Now, you know someone who is age 36 who looks like she's 72. You also know someone who is age 36 who looks like she's still 18, and vice versa, and upside down, and it always works that way. But you see a lot of people that are age 36, you're like, yep, they look like a 36-year-old. Cracks me up. One time a couple years ago, there's a gal who I knew is my age, and I've known her for a long time, know her husband well, I taught her kids, and we were talking, and the dinghead and I even went to college for a year together. We're literally the same age. Oh wait, she's 2 weeks older than I am. But anyways, she was offended that we were talking. Mind you, I know she's my age, and she was offended that this was like 3 years ago. She was offended that I would have guessed that she looked 43. I'm like, well, for starters, you totally look 43. Honestly, I think she looks a little older than 43, but whatever. But I gave her the benefit of the doubt because I knew what she looked. And she was offended by that. I'm like, what are you talking about? I mean, you are 43. Of course you look 43. Now, there are some people that you know that are, older, like say 43 like me, whatever, and you're like, boy, they really look good for their age. They do. Now, I have a friend of mine, there's a gal I went to high school with, and she started fake baking, tanning, whatever, in 1987. And I remember at the time going, gee, she's going to look bad when she's the age we are now, right? Well, she works in Hillsboro. She still lives in Hillsboro over here. I see her from time to time, and wow, you look at her and you're like, yeesh. Well, all that tanning has not been good for her face. So when you look at her face, even though I know how old she is, I would guess she's a little older looking. A lot more lines because she's been out, well, not been out in it per se, but she's been doing that tanning for all these years. So of course there's always going to be variations. So what regression says is, yeah, we have this idea, okay, that we have this y equals, I'm going to write it like this, y equals mx plus b, right, that slope. This is how many freckles or tan lines, laugh lines, whatever you're going to call them, you get on your face per year, times how old you are, plus some initial amount that you started with, plus what we call error. And now I'm going to write it with big E. Now this error is that idea that everybody's different. There's always some error added on. And that error, this is part of the regression analysis or regression theory, is that those errors are normally distributed with a mean of 0 and some standard deviation. Okay? And so the idea is that there's always going to be some error that you're going to add on to this amount. Again, this is y equals mx plus b. So what I'm going to do is I'm going to generate some errors here. And when I generate these errors, I'm going to be a little bit careful in that I don't want them to be so weird that it throws my data off, okay? Because I'm only adding a couple of lines per year. I don't want it to be such a weird thing that it completely throws my stuff off. I'd like it to be such that it just changes what my graph looks like just a little bit. So over here I'm going to say equals this, which is y equals mx plus b, plus this. And then I'm going to go ahead and truncate that, which is called truncate. I'm going to get rid of the decimals. You could show less decimals, but what happens when you show less decimals, and it's not a big deal, but if you do, they're still there. It doesn't look like they are. So, in other words, this data is data that you would have gathered. But when you graph it, this is what's going to show up when you look at the graph. When you look at the graph of this, it's no longer going to be a straight line because I've added those error pieces in. Now notice how it is still pretty straight line, yes? It didn't change by a whale of a lot. And so if you do this, by the way, this is 113 tan lines, or laugh lines. That's kind of ridiculous. Now, there it is, and you're like, wow, that couldn't get more straight if I tried. Again, I was screwing with this data because I want this data to come out to be, you know, something interesting, or at least what I think maybe better, maybe. So I'm gonna monkey with this a little bit more. Again, the idea here is I want you to see that these errors are what makes the whole thing go. Without these errors, this thing looks kind of crazy, actually. See how everything updated? Boom, boom, and a boom. These didn't update though, so I'm gonna grab them again. Copy and paste. Special. Now I'm going to look at the graph. Again, the idea being here is any idiot, once you have the data, can go, oh, well, let's graph that real quick, and we'll find r and r squared and all that good stuff. And that's what I'm talking about, people. Look at that. Is it pretty much a straight line? Sure it is. Is it? Can we be pretty sure that, hey, the older you get, the more lines you're going to get on your face? Yeah. Is it going to be perfect? No, because some of these points are off the line. You see that? And yet, when you look at it, they're all pretty well clustered tight to that line. Okay? Now, clearly, if a person wanted to, he could find a correlation by simply taking the square root of 1.277. What are you doing? 0.981 rather. Sorry about that. Pay attention to what I'm doing here in a minute. And of course that is positive because it's got a positive slope. Okay. Now again, I can test that with my t-test. So it's equals r divided by the square root of 1 minus 0.981. 0.981. Need other parentheses right here though. Close that, and then divide by 1 minus, or n, which is 50 minus 2, so divide by 48, and voila. Okay? And that is a t distribution. That's a t statistic of 49. Okay, well, you don't need to be a rocket surgeon to see that, hey, if this is bigger than um, plus or minus 3, you're rejecting H naught. This is hugely significant. Okay, and anytime you have an anytime you have an R squared bigger than about 0.81, it's easily going to be significant. But again, you can actually have an R squared that's significantly lower than that and still have a significant correlation. I'm just saying, as a rule of thumb, if I get a correlation R of 0.9 or negative 0.9, I am guaranteeing you that is a significant deal. I'm just saying there are times when you will actually get a lower correlation that's still significant, i.e. on the last one we did a few minutes ago. Okay? Now, so what a person can do, of course, is come back up here. Okay? And so what we've got is we can fit our fits in here, or our approximated values, and it's equals, so 1.277, that's right from the graph, times our x value plus 1.8332. Now, remember, we can't add the error because we don't know what the error is on every single function, okay? All we can do is graph the best line of best fit. So I'm predicting it's 24.8. It's actually 25. Hey, that's pretty close. Okay? Copy those down. And then come over here a ways and let's go find our residuals. Now our residuals, again, I can just go equals the actual minus the approximate. And so you notice how we underestimated just a skosh because the actual value is above the line. And then here, we're overshooting when it's negative like that. Okay? And so there it goes. So no big deal. These are our residuals. That's what it's saying to us. Now again, look at this guy right here. Okay, that's saying that the blue line, we're saying that the blue dot is above the line. That's what it's saying to us. Okay? And this is saying that the blue dot is below the line. How far? 5.9 below the line. Okay? And by below the line, we mean straight up the age 30 line right there, or age 20 line, right up to there. Okay, so that's the game. Again, I can make a residual plot all by myself, or I will show you the other thing as well. So highlight those, hold Control down, click on your residuals while holding Control down, insert, scatter plot, boom. There are my residuals. Notice how they're all over the map. And it doesn't matter if we're lower or higher. It's basically the same spread throughout. That's a big deal because that says to me no matter where I am, I'm going to get a pretty good approximation. There's no better on one end, less better on the other end. It is just pretty good throughout the whole range. Okay. If I specifically asked you, oopsie daisy, I said, hey, can you predict for an x that's equal to 85? Well, sure you can. Notice here it is right here. I just copied this guy down. That is our actual function. So if you're 85, you're going to have 110 lines approximately on your face. Now, can I predict for age 112? I can. I can. Does that mean there's going to be a good fit? No, and here's why. My last data point was 86. Now, if you asked me to predict for 87, 88, 89, 90, I would feel pretty confident about that. But if I go out like 22 years from there or something, or well, I guess that would be 16 years from there, that's quite a ways out. A lot of things can happen. I mean, you could really turn it into a sour, grape, shriveled grape, after you turn 100. I don't know. Lots of different things can happen. And so we call that extrapolation. It's that idea that if you go too far away from your data on either end, either way higher or way lower than your data. Our lowest data point was age 18, which was probably still kind of screwy. But if I went down to like age 5, well, age 5, ain't nobody age 5 has wrinkles on their face to speak of, so that's kind of goofy. So you'd have to be careful of that. So this is what we do. You're predicting for values of x way, and that's kind of a weird term, but way outside of the data that you built the model on. Now, from a global warming standpoint, the the thing that's always bothered me more than anything else about that, besides maybe the fact that the WHO studies it gets the big research grants and whatnot, but the thing that's always bothered me more than anything else about it is from a statistician's point of view. We have global temperature data, fairly accurate-ish, for a good share of the planet, let's say 100 years, and that's a stretch. Because for years, we didn't have any data for large swaths of the Earth. There's large swaths of the Earth where, we don't know what was happening because A, no one lives there, or B, the people that live there, they didn't have thermometers to pay attention to that stuff. They didn't care. Record keeping, iffy. All kinds of stuff like that. Now, in the late 80s, early 90s, they started collecting temperature data from satellites, which at the time people were like, people that didn't really understand how that stuff works were concerned that those aren't going to be as accurate. But then over time we realized, yeah, they're more accurate as a matter of fact. And we got satellite coverage over the entire Earth, including over the oceans and what the oceans are doing. And so as a result, we can actually have a better picture now than we did back then. But okay, let's say it was back 100 years. So you go back, way back, you have to rely on other things, tree rings and other things, some glacier material, things like that, to try to establish temperature. Well, if you're going back far enough and you're like, well, of course there's going to be error in your measurements, and you get a little bit of error, throws things off by quite a bit when the measurements aren't that big to start with. Also, if you go out far enough, so let's say people say, well, in the next 200 years, a lot of things can happen in 200 years. So you've built this model on let's say maybe 100 years of good data, plus some approximated data further back than that. Now you're going to tell me what's going to happen 200 years from now? Man, that's going to depend on so many things that yes, you can plug it in and get an answer out. It could be completely ridiculous. Okay? Extrapolation is the four-letter word when it comes to regression. We do not want to do that. Now, again, feel free to mess with this because we will be messing with the regression tool next week in class, actually. I think it's next week in class. But we'll see. Again, so my X's, my Y's rather, are in column B. So I'm going to click on lines on face all the way down to this fella here. Make sure you grab the same amount in A. Don't go down to the ones I predicted for. That's dumb. And yeah, again, here we go on all those plots. The ones I want. Boom. There they are. Nice. And there's my residual plot again. Again, up here. Okay, there's our R. There's our R squared. Bam. Talk about adjusted versus R squared a little bit maybe later on. We'll talk about that. Standard error, this is going to be a big thing coming up soon. Not today, but coming up soon. Hey, look, there's our F. There's our significant. That's our p-value right there. The p-value is 5.9 E minus 43. Highly significant. Again, this comes from an F, not a T this time, but that's okay. Okay. You might remember, what was our T on this last one? 49. Interesting. Let me pause one moment. I was going to say was this. The T that we found on the previous page, 49.78. And then T over here, this F statistic that they generate over here is technically if you square root it, you will get the T, approximately the same T value as you found doing it the other way. Okay? It's neither here nor there. It's just kind of an interesting thing. They are very closely related. And we will use, from now on, going forward, if it's just a simple linear regression where I have one X and one Y, I will always use just a T distribution. Okay? However, if it's a what am I trying to say? If it's a multiple regression, which we're going to talk about coming up, we'll actually always use this setup right here. Okay. Notice that down here, age, that's the slope aspect of it, right? In other words, there is a slope. As age changes, so does the wrinkles on your face change. Look at the p-value right there. First of all, look at that T statistic, right? It's the same T statistic we computed. They should be identical, but I rounded this off a skosh because I typed in 0.981. I didn't give it the full amount, right? That's where it's off a little bit. But look at the p-value from that. Hey, it's the same p-value. It is the same p-value. So, in other words, it's very important. Age, in this case, is determining, or it can explain why you have more lines on your face. Okay, it's not some random deal. Now, intercept, don't worry about this p-value. Never worry about this p-value here. It is what it is. You just ignore that part of it. So, it's really just this p-value here is the one we're interested in. But again, this t and this p are the same ones that you will compute when you do that. Is the correlation significant? That's the same one you will be computing. Okay. Again, this is perfectly good throughout. So regardless of whether I'm predicting for age 50-year-olds or 80-year-olds, I'm going to expect to have the same basic amount of error on either side of it. Okay, there's not going to be worse or better on either end. Okay. Now, my next one I'm going to do, I'm going to purposely set it up so that I have a situation where I have more error on the upper end and then on the lower end. So I'm going to pause you for just a second. All right, here's some good data, right? There it is. I don't know what X and Y mean. I don't really care, but I made a scatter plot of them. I'm going to go ahead and format a trend line. Boom, boom, boom. Hey, that's pretty significant. That's cool. Let's find the correlation. So equals square root of 0.6671. A correlation of 0.816. That's pretty good. So I'm going to go ahead and take that, divide by the square root of 1 minus 0.6671 divided by, there are 18 degrees of freedom, I think, there. What is your problem? P divided by the square root of, I swear I put it there. What is your problem, you piece of garbage? Just leave me alone. No, it's not that. It's 18. Oh, I didn't put an extra parenthesis. This is in there. There we go. So I got a t value, a t of 6. Well, clearly that's significant, right? Because a t, anything bigger than 3, you're rejecting h naught. There is a correlation. It is significant. Now, again, you're welcome to use the regression tool. I highly recommend, again, you get comfortable with it. Here are my y's. Here are my x's. Notice that this time I did not include the labels. I really should in this scenario because I really would like to know what's going on with them. Boom, boom, and voila. Notice the residual plot this time. I'm going to make it a little bit bigger so you can see it better, I hope, maybe. What do you notice? As you get out this way further, there's more error than there is when you're back here. So if I'm predicting when x is 10, 11, 12, 15, I'm going to get a good prediction. As I head out around 20, 18 to 25, it's going to be a worse prediction because these residuals are getting bigger the further I go this way. It's not a problem. You can still do it. But remember that when you're predicting that you're going to be more error in your prediction on this end versus on this end. Now, remember we said we got a t of 6? Well, the probability of that is 1.1 e minus 5. Now remember, you can do that by doing t equals t dist of 6, comma degrees of freedom. There were 18 degrees of freedom this time, and oops, I lied to you. Don't do that. I want t dot dist. There's a couple ways. There's about 18 different ways to do these, all right? So I could have done it that way, kind of, but this is the way I've been doing it, so I'm going to stick with it, okay? And this is an upper tail, right? So I'm going to do 1 minus because that 6 is positive. So 1 minus, and I'm going to take that and times it by 2. And this is how that p-value comes about, this p-value right here, okay? Again, same p-value as this. If you square root 36, you're going to get 6. Boom. Okay? Everything's 100% exactly like you thought it would be. Here's my equation. Y equals 1.3x plus 42. It's literally what we have over here. Bam. We can predict, so the fits. Okay, the fits, of course, are going to be what? Equals 1.3 times these guys plus 42, roughly. I'll round it off close enough. And then the residuals equals this minus this. Bam. Okay. Bam. There it is. Okay. And of course, that's where they got the residual plots, from. So just be aware of that. We're going to talk about this a lot more in depth next week. So you're going to be asked to, in this section, this is 10.3. They're going to give you some of the basics of it. They will give you the giant equations. For goodness sakes, I told you, I'm telling you again, do not, in any way, shape, or form, do I want you to do, in no way do I want you to do their equations for finding that. Okay, the equations that they talk about, the sum of the x, y, that's not what I'm asking you for. So you're going to ask, find the equation of the line, and they're going to ask you to predict for a particular value. Okay, only predict if it's significant. If it was not significant, if it was all over the map, well, like this one. Oh, shoot, dummy. Watch me just make some data up here. Oops, that would be stupid. So 19, whatever. Now, if I went over here and I said, all right, data analysis, I'm going to generate some data, but watch how I do it. Random numbers, yes, I want 10 this time because I only want 10, I guess. And I want the average to be 110. I want standard deviation to be 30 or something ridiculous. And the output range I want to be right here. And voila, there they are. Now if I graph these guys, you know what's likely to happen when I see this? Judas Priest, it's all over the map. And when I graph this guy, if this turns out to have a good correlation, I'm going to be upset, but it doesn't really. So there it is. What you're going to see is you're going to have this kind of a deal right here. The idea being the correlation is the square root of, again, square root of 0.2 oh yeah, by the way, it's going to be negative, right? So 0.2133. So it's 0.46. This correlation may or may not be significant. Okay, later on we talk about this, it may or may not be significant. And you can test that, but of course it would be negative. Why? Because it's going downhill. Okay. Now watch me change this one right here. I'm going to make it a little bit smaller because I can. I'm making the data after all. If this were the case, look what's happening here. Now I have an r squared of 0.07. In other words, my equation's only explaining 7% of what I see. And so that means you get an R of 0.26. This will not be significant, I guarantee it. And then look at this. I'm going to make this guy a little bit smaller yet, that 134. I'm going to make him even smaller yet. You cannot get more of a flat line than this. Anyway, the point is, there would be no reason to predict from this. If this correlation is not significant, then don't predict. That's as simple as that. Do not use this to predict something if it's not a significant relationship. Don't ever do that. Okay? Now next week we're going to talk about multiple regression a little bit. We're also going to continue talking about the ideas of the errors in this situation. We're going to talk a little bit more about residual plots next week as well. And then also about outliers. So this guy up here is clearly an outlier, but we'll talk more about why this is an outlier versus this one here, the one I kept moving. Initially, this one up here, I had leverage, or it was an influential point. Why is that? Because you see this one's right in the middle of the distribution. All it's going to do is make the whole line shift up and down. But because this one's on the end, it takes and pulls the line up, which really tips the line up or down accordingly. So I changed this 1 point down, it made all the difference in the world. I didn't change anybody else. This point, whether I change it or not, notice that this one is, oh shoot, this one is this 161 one. Watch what happens to our data if I change that one. If I can find it, it's right here. What happened? Basically nothing happened. You see that? basically nothing happened. Didn't change hardly at all in terms of the slope-wise because it had no impact on anything. All we did was just it shifts the line up or down a little bit, but it had no impact on the slope of the thing. So we're going to talk more about the influential points next week and points that have what we call high leverage versus just outliers, and talk a little bit about that sort of thing. Be nice if you could just get rid of all outliers, but let's face it, I mean, that'd be getting rid of all of Portland, right? No. The idea here is that whenever you have outliers, sometimes there's a reason for that. Was it bad measurement? Was something broken? Were there any sort of things in the questioning that could have biased the situation? People lying to us. But usually, in the real world, in a scientific situation, if you have something that stands out, something's broken, machine, maybe our testing equipment, something may be broken, you might want to go look at that. So we'll pick rest of that up next week. Not next week, the week after.